It is December 16th, 2025, and this is the bi-weekly libhal meeting. All right, for our agenda today, and actually one thing I want to say before we go on, this is probably going to be the last meeting we will have for this year. I don't expect to do another meeting this year. But yeah, there's some pretty cool stuff that's happening on the last little meeting here. All right, so the agenda items. First one's going to be talking about a particular pattern that I have implemented myself multiple times before, and I thought I'd just kind of describe it. It's basically trying to reduce the number of VTables you have when using templates. We'll go into that in a little bit. Next, we'll go over some updates to the Kona config 2. I'll also go over some libhal CI updates, which will not really improve performance of anything or improve the speed in which CI works. It actually makes it a little slower, but it'll improve the overall amount of time used. I'll go over some updates for llvm-toolchain, which is basically that we have full support for ARM Cortex machines, architectures. I'm also going to be talking about focusing libhal-exceptions, cutting it down to just the things that really make sense, supporting LLVM with libhal-arm-mcu, and then finally we will talk about libhal v5 updates. All right, so let's talk about VTable factoring pattern. I named it this, so if you look this up anywhere else, you probably won't find the name for it. Maybe this is obvious for some people, but I think it's something that's worth describing. So here's a little example. I want to make a memory resource, a polymorphic memory resource, PMR here, and we don't really care about what scheme we're using to implement the memory resource, to implement this allocator. But we will state that the memory for that allocation is embedded inside of the object itself. Maybe some other variables to track things, but the overall storage will be embedded into the object itself. So what's the issue here? Before we get into that, first I just want to make sure we're on the same page when it comes to what this interface is and what it involves. So in C++ 17, C++ introduced memory resources. They are basically ways to create allocators that use runtime polymorphism, or basically get dispatched at runtime. They are designed to be a means to allow a vector or a container of some sort to work with a different type of allocator. One issue that existed, or still exists with C++, is that if you have a vector and you do create your own allocator type and you pass it into the vector, you can no longer pass that vector into any other vector. So if you created your own allocator to do a very special thing, you cannot pass this to some other vector that takes no allocator argument, because that vector takes the global allocator object, basically the standard allocator. And if you have two separate allocators, you can't pass them in between each other. But with PMR and polymorphic allocators, so long as you implemented those polymorphic allocators, you could work with pretty much any of these. So it got rid of this little issue here. But with this, we also got the ability to just make general purpose allocators for whatever we like. It came with a lot of bells and whistles already built in to make it really easy to use, in my opinion. I really like it. It's a really cool design. So why is the previous example not acceptable? And just notice that I'm not writing down the do is equals just because it's just to save space on the slides. This is all slideware, so there's probably some things in here that might not be 100% correct. I'm pretty sure it is, though. But yeah, so consider what happens if we make two example resources, these little examples here, with different memory sizes. We can look at this example here to get an idea. And I think I already have them up here, but I'm just going to use the links. So I've actually provided a couple of other answers here, but if we scroll down and we look at just example resource here, if we look at the disassembly, we can find their VTables. So using, in this case, Clang. I think I was using GCC before. Must have been, yeah. But anyway, we have example resource 32. We have example resource 16. If we look at the main, we actually have 3 different variants of this resource. So 16, 32, and another 32. So what you're observing here, for those who may not be as familiar with this, is we're getting two different template instantiations. We get one for 16 bytes, we get one for 32 bytes, or 32 for the memory size. Now, because we've already created one of these objects for the type 32, example resource 32, we will only pay for all the unique variations of this. But if I wanted a resource from 1 to 15, then I'd have up to 15 different resources or unique types. Now, what does this end up doing? It does a couple of things, and I might be getting a little ahead of myself, but if I control click on this, I can actually jump to each one of the different functions from example resource 16. Going back here, you can see that just by looking at some of this code here, using some context clues, we can see that we have example resource 16 : do is equals. If you look down here, we have 32 do equals. What's happening here is that we're getting a new instantiation, a new copy of each one of these functions for every single one of these different template parameters. I go to do is equals here, you'll see that it does almost barely anything. And these functions don't do anything at the moment, so they're empty. But if they were full of an entire scheme of doing something interesting, then these would be full. And you get a duplicate of these for every single instantiation that you have that's unique inside your entire program. Let's get back over to this. Let's go back. Yeah, so you get a new VTable for every unique memory size. I already said that if they're matching, then they get the same VTable. And yeah, so I kind of already explained this bit. And then here's the cost. So if we were to think about this, there's going to be at least one implementation of example resource. There's not going to be one. So what we're really looking at is how much is the additional cost after you've created the first one. So that's n-1, where n is the number of unique variants of example resource, so 16, 32, whatever it might be. Because the VTable has 7 entries, it's 7 times the number of pointers you have. These are all just like pointers for a 64-bit operating system. Sorry, architecture. Then we're just going to add, and I think I have the parentheses correct here. I think so, yeah. You're going to just add the cost for each one of the VTable functions. So for each one of the destructor, do allocate, do deallocate, do is equals, each one of those that are different between these two, you add all those up. Assuming that they're all going to be identical, because I doubt the template instantiation value here is going to make much of a difference for whatever scheme you choose. These are going to be around about the same. The problem with this is that we have duplication of VTables and duplication of functions that aren't really giving us any benefits. Not like, in some cases, we could imagine that knowing the size of the overall capacity at compile time can allow us for certain types of optimizations. But I would even say that, like, yeah, that may be true. And it could happen. And if you measure and it does that for you, great. But I think in most cases, we should just concern ourselves with making sure that the operation works versus all of this. So what can we do? Well, a couple of things. One, we can actually extract out the base class to its own base class. So we create a base class, it's not templated, and we make it inherit memory resource. Rather than holding an array, it'll hold a span of the buffer. And then this is all slideware, so it's kind of condensed. I would have probably used the proper constructor here or whatever, but basically we will take that M buffer, or storage here, and we'll assign it after construction. That way, once we start actually using the allocate and deallocate functions, this is already initialized and we can go from there. And the lifetime of this is bound to the lifetime of this object, and this object has greater lifetime bounds than this guy. So everything here is safe. It should just work. Yeah, that should just work. When you look at the VTable, there has been some improvement. I think actually, has that not changed? Okay, so this pointer has not changed. So none of this stuff has changed. Daisy. I did remove RTTI in this example, so that just was one little change that's a little different here. So maybe this entire area should be shaded yellow for no change. For the VTable functions, all of those got swapped out with the example resource base. Because we don't override them in this implementation, we just get those. So now there's only one implementation of do allocate, do deallocate, and do is equals, and we're pretty much, and then that's it. There is one thing though, and that is each of these objects needs to have its own destructor. Now, a lot of times these destructors are trivial, but they might not be. This might actually have some sort of non-trivial operation that has to do. So on top of this thing having its own destructor, this object on top will also have its own destructor as well. So we still have to have a unique VTable for each one of these because we need to record the unique destructor in the VTable as well. So now the current cost at this point is n-1 times 7 pointers for the VTable plus the ROM cost of each one of your destructors. I'm not counting the cost of this because it's the -1 part here. We've already going to pay for this once. That's fine. It's really about how much do we pay after we've paid once. And now we have to pay for the destructors on top of everything else here. To some degree, they're identical, and you can use some linker commands in order to combine all of those duplicate destructors and functions. But for now, we're not going to worry about that. So what's the next move? We drop inheritance. I spent some time thinking about this because I actually thought that this was the solution or a good solution to this problem. And then I realized that we're still dealing with this VTable that I didn't want to exist. That just goes down to how C++ works, or how its object model and inheritance model works. And it makes sense given what you need to know in order to make these things happen. So the answer that I found was to eliminate the inheritance altogether, to put the base class as a member, basically use composition, and then take your storage and assign it directly into this object. Maybe I would call its constructor and then pass this object into it. That could be an idea, rather than using the slideware. And I was actually fine with this. I actually didn't see any big concern. There's just one part of me that really wanted the ability to pass this object into functions that take memory resources as pointers and as such, or take polymorphic allocators. So if that's the only thing that I really wanted after this, because I have a resource function that you can call in order to get back that resource and pass it around if you want to. But in order to make this work, I actually added in some operators for implicit casts. So if you try to assign example resource 3 to something that takes a memory resource pointer, this will just automatically just pass along its internal pointer. Same thing with polymorphic allocator, does the same thing. Except this one actually wraps this type. One thing that, actually, you know what? Oh, yes. So one thing that I was also considering, because we have strong pointer as well, is if I used enable strong from this for this object, basically enabling this thing to be able to point to itself and have its own methods point to itself. I could also consider having another operator overload for conversion into a strong pointer of a memory resource. That way, we can keep lifetime bounds for this object alive long enough for all references to its example resource to be destroyed. And then you can kind of see that here. So here we have this, and let me turn off link binary. We have resource 3 here. And what you'll notice is if I look for a VTable, if I do VTable for example resource 2, you will find those VTables. That was the other case where we had removed the base class, factored it out. If you look for 3, you will not find it. And that's because it doesn't have one, because it doesn't have any virtual APIs. If you look for resource base, you will in fact find its, and it's what you'd expect. The one thing that you do get, though, is a destructor. You still have a unique destructor for each one of these. And I kind of hate these destructors because they literally all do the same exact thing, even though the type definition is different. So this is one of those things that could be optimized away. And I would really be sad if the destructor for this was actually non-trivial and needed to be stamped out for each one of the different numbers here. So that's one little annoyance. And I think that is pretty much it in terms of what I wanted to kind of talk about. All this really comes down to is there's going to be times where we're going to see a template with some APIs that are virtual, and we're going to want to de-virtualize that. We want to pull those things out. We want to abstract that stuff away, just because we don't want to get those additional VTables created. And again, I don't think those additional VTables being created are inherently a problem. I think there are use cases where you'd want to have a template of something that has a virtual API, but specifically when you want each instance to be unique. Like if you had unique types, those are all going to be generic, so those need to be different. But in this case, we have a unique size, and we want to actually have ownership, have it be contained inside the object, so we need to have this information there. Now, once we do that, our cost goes down to basically just the cost of the destructors, and that's about it. The libhal policy for this will be, when possible, avoid non-template or non-type template parameters like size or structs and all that for template classes that inherit classes with virtual APIs. Specifically, things like size, where the numbers are broad, you expect people to put in arbitrary numbers. So you expect that there would be an arbitrary number of unique inputs that they get. And from there, you can have a lot of bloat just from adding in all of those different instantiations. If you want to use VFP and you want the inheritance-like usage, you can use implicit conversions. I actually don't recommend you overload the error operator or the asterisk operator for a couple reasons. One, you can't overload return types outside of implicit casts in a way. So you would only be able to get one of these for one thing. Also, it could confuse your user. If a user takes an object that's an L value that's absolutely not a pointer or a reference of any sorts, and then starts using these types of APIs on it, and it's not a smart pointer, and it gives it back something that isn't, like, I don't know, between memory, I mean, I guess I give back a memory resource in this case, but I can also give back a polymorphic allocator. Yeah, it's just one of those things where, like, if I have more, and if there's a case where I have more than a couple of objects that I can extract out through casting, then this would fall apart. So that's why I recommend just not really even touching it, unless you're writing something that needs those things. Cool. All right. That's pretty much it for VFP. Hopefully you guys learned something from that. If you already knew your templates pretty well, it's probably quite obvious. But it's one of those things that I think is overall a useful little technique to just think about why templates are problematic with virtual APIs. All right, Conan config 2 updates. I have added Mac, Linux, and Windows OS profiles. Before, you had to put in like Mac_ARM or Linux x86_64. Now you just have Mac, Linux, and Windows. What it does is it automatically detects your architecture and then just puts it in. So if you were trying to cross-compile, then you need to do Mac and then whatever thing you wanted to compile to. If you are just trying to build on your machine, you just do -pr Mac. And if you are just trying to build something on your machine, you can also just do -pr default, and it'll work as well. I removed the llvm-19 compiler profile from Conan config 2, mostly because the ARM fork is in a old deprecated repository, has a couple of issues, and I decided that rather than trying to fight and make an older version of LLVM work, I'm just going to focus in on the one that I know I can get to work really well, which is llvm-20. So that's the only version we currently have. I do have a PR out for 21, but I'm having a couple of issues. So either I'll get to that at some point and get those in, or maybe someone else will take that and pick it up and will help it. I pretty much did everything except for solve the last problems, like yeah. So the rest of like getting the files and setting things up, like that's all done. And then finally, I've added in HAL bare profiles. So these are profiles that have the OS set to bare metal, and they just have the architecture set. In this case, we have Cortex M0+, Cortex M4, so on and so forth. I'm actually going to say one thing before I move on. I noticed, I forget where I saw this, but I saw some other project that was using Conan, and they had set the architecture to ARM v7. and they just build their applications using ARM v7 as their architecture, and they have their profiles inject additional information about like what cortex they're using, that kind of thing. I thought about it. I spent some time today thinking about, is that the right, better choice? But I actually looked into this before, so I'm actually just going to restate why I went with the choice of having separate architectures for each one of the different Cortex-M processors. Their instruction sets are different. I mean, M4 and M4F are different, and I don't think it's actually possible for us to pre-build binaries, and then some of them have hard floating point unit operations, and some of them just don't. Like, I don't think that's going to work. So it's too broad of an architecture name to represent all the different architectures that we need to support. And actually, with some of the things I've figured out with LLVM, it would actually be a disaster. So anyway, we have all these bare metal architectures because that's how many ISAs we have to deal with. Just for anyone listening who doesn't know what an ISA is, instruction set architecture. Basically, it's just the commands that the CPU can, the instructions that the CPU can understand, and they're different as they upgraded them over time. Oh yeah, and the whole point of the bare metal profiles is if you want to build an application, or sorry, an application, build a library, but you don't really care to even specify what MCU you're doing it for. You're just like, no, I want a Cortex M0 Plus. I want to build it for that. Then it'll build it for that thing without bringing in other baggage like platform name and that kind of stuff. Alrighty, libhal-CI upgrades. This used to be like, I don't know if I remember correctly. It's like, it was this many package and uploads, and then on top of that also like 17, 15 more Cortex M0 VMs that were instantiated. So what I've done is I've consolidated all of the Cortex building stuff into a Cortex M LLVM and a Cortex M GCC. There's a single command that can basically build out bare metal operating system or bare metal architectures. You can just specify a list and it'll go through it. The reason why I did this is that having so many different VMs in parallel just ends up using a lot of resources. And one of the things that I was looking into was if GitHub tomorrow decided that they wanted to start charging people who had free accounts, and they wanted to start charging them the same amount they had for private accounts, basically pushing everyone into private accounts, which has happened with a other CI system I used in the past, which is called Travis CI. If they did that, what is my bill going to look like? Because it's important to not get, just a random bill sent to you going, oh, all right, I owe 10 grand for what reason? Oh, it's because I tested the CI across my entire organization multiple times to make sure that the CI works, that kind of thing. So I've been looking at optimizing libhal-CI in order just to make it more robust, but also to make sure that it can also be more efficient. This overall takes actually a little longer for you, just because we're going to do all of these builds serially. This allows me to not have to do, one of the main benefits of doing this is that we download and install the compiler once and then continually build from there. Same thing with GCC. Versus each one of the different packages having to download their own version of the compiler. I knew it was wasteful from the beginning, but it made my life much easier to just do it that way. Also, I don't know if I talked about package and upload all, but basically this is going to become our new deploy.yaml script. And it's just going to be what you throw onto any one of your projects, and it'll, or sorry, not any of your projects, any of the libhal projects or libraries. It builds for Mac, Windows, and Linux, and it also builds for the different architectures x86 or 64 and ARM. So we will actually have pre-built binaries for almost everything that you'd care about. Then we're also going to do pre-built binaries for all of the Cortex and processors architectures as well. So in the future, before whenever you wanted to build for Mac or Linux or whatever, you would need to put in build missing, because I never built libraries for those. But now I'm planning on doing that going forward. You still probably need to use build missing for like the next month, I would say, but hopefully soon you won't have to do that as much. Because GCC doesn't support modules enough to do what we need, there is a module support needed flag that you can add in, which will disable using GCC. Will not build the GCC. That's why this is for strong pointer, which uses modules, doesn't have a build for GCC. GCC 15 seems to have a lot of fixes. I'm waiting for ARM to come out. Ooh, I need to check their website because around December time, they usually, Christmas comes early and they put out a new version of GCC. So 15 might be out. I can add support for that, and then I can see if modules actually work for that, and I can bring them back. And then this particular flag may not be as necessary because I'll pin the GCC version to 15 if it works well enough. We also have coroutine support. This one's odd. I did not expect this at all. But LLVM, or specifically LLVM's linker, will crash, and it'll give you a nice stack trace when you attempt to build with coroutines using Cortex M0, M0 Plus, or M1. Something about those, there's like some messed tail call optimization thing that doesn't work for these for some reason, and it freaks out because it can't do it, and then it stack traces. But these were needed in order to allow strong pointer and async context and libhal v5 to actually build. And yeah, so that's pretty much that. Okay, focusing libhal-exceptions. Libhal-exceptions supported and currently supports native exceptions and Estelle exceptions. And it had two main features that it added into it, which were both mistakes, and I'm going to explain that. Number one, it had a terminate handler setter and also an exception allocator setter. Couple of things. One of the main reasons why I made libhal-exceptions was to actually be a very quick way to get to inject the terminate trick into your code. Basically, what it does is it will replace the terminate handler, the default one, such that you'd get that binary cost reduction, because the cost that you get from GCC and LLVM, which I'll talk about later, just comes from doing a verbose print statement, and that's where a lot of the bloat from exceptions come from. So I had that in there, but the reason why I didn't like it, I realized recently that I didn't like it, is that I was going back to start refactoring some things, and I realized that the terminate handler is wholly orthogonal to exceptions. It is part of the exception, it's part of the exception header, obviously, but it's really just another abort function. It's something that you can call anywhere in your code, and also somewhere we call throughout exception. Basically, my exception runtime doesn't care about what you set terminate to. I don't actually need to overwrite it. There's no aspect of Estelle exceptions or libhal exceptions or anything that I've built that really needs to override this. So what I realized is that I could just do the overwriting in libhal-arm-mcu, just put it directly in there. Or even better, just make a separate library purely for this trick and not confuse libhal exceptions with it. So that's why I consider having this setter here to be a flaw. But I'll get into that in a little later. I should come back to this in a sec. The exception allocator setter was probably even worse. I got asked after my talk at CPPCon if I could reconsider my design for the exception allocator. What the individual said was, you are basically adding in overhead for the polymorphic allocators. I'm like, oh, well, I mean, it's not that. Polymorphic allocators are not that much overhead. And then he responded back with saying, well, no, I have a system that I'm working on that cannot use functions, and that was a weird way to say it. And eventually what happened was that he has a compiler that I think he's designing or helping design that has some limitations at the moment, and having to deal with polymorphic allocators just adds in a lot of additional complexity. But here's one of the worst parts about this whole thing. A runtime setter assumes a default. If you have a setter function that you call sometime after main has been called, that means that something was either there to be the default, or it's left blank and it's a foot gun. that if you don't do the right steps first, will blow your foot off. So if no default is provided, then the API must be called before any exception is thrown. This is problematic. This is a shoot your foot off problem if you forget this, because now you're prone to failure because you now need to remember to set this up. Or there must be a default implementation such that if you don't provide one, then we will provide one. But the problem is that now you're kind of back to the terminate handler issue where we're now bringing in dependencies that people need to strip out in some way. Also, the PMR allocator to forces VTable overhead and requires you to have an object. And even though deep down it's not that expensive, I mean, hey, I already showed you, what we did in order to get rid of all of this. So here's where the real move is. A couple of things. Going forward, libhal-exceptions will only support the exception runtime implementation, and that's it. It'll call it to terminate, and it's up to your platform that you're developing for to implement what that means. And that's pretty much that. One more thing I need to bring up here that I did not write down in this. Another big mistake for the exception allocator setter, specifically for the native builds. What I did was I actually overloaded the CXA allocate exceptions function. I did that for the user as well. And when I do the allocation, I actually guess the amount of bytes that the exception object needs. I know it's 128, and I think it's probably still 128. Probably haven't changed it in a while. The problem is, if they change it, now they've broken my ABI because my ABI just assumes that it's 128. And it's not also very shrunk wrap. It's using up a lot of memory. This is all to say that the approach of overloading the native exception handler or exception allocator is flawed. And it was cool just doing it before, but now when I want to make this a little more serious, it's a problem. All right, so we can add support for to compilers that do not have support. So one thing about this is that if the idea here is that when you bring in libhal-exceptions, it replaces your exception runtime. And it is not a way to also allow native exceptions to work slightly better for your use case. No. If you want to modify that, you should manage it on the compiler side, recompile it with your desired changes, or use wrap and other things to overload those things inside of your platform. But libhal-exceptions won't be a part of it. We'll also be using libhal-exceptions to add exception support for platforms that don't support it. I don't have anything in mind at the moment of a platform that doesn't support exceptions that we would need to add support for. But if it comes up, we can do that. Custom exception allocation support. This is something that I went to that individual and asked them, hey, does this fit your needs? And he's like, perfect, this would do it. In C++, you are allowed to override the operator new keyword. You're able to control what it does. If you don't want it to call malloc, you can have it call your own API. You need to specify just one of those in your binary and it gets linked in. I'm planning on doing the same thing, but for our own allocator object. So you'll have basically some sort of allocation tag that will disambiguate between what new and delete operation you're calling. And for libhal-exceptions, that will become a weak reference. So you now get the ability to implement these yourself in your application, and then you get full control over how this is done. With this idea, basically, the moment you make your own implementation, you scrap ours. We can give you a default implementation, but the moment you make your own, ours gets scrapped out completely. My hope is also to somehow make sure that if you implement new, you also are forced to implement delete, so that you don't end up implementing one and not the other, and you have some weirdness happen. But yeah, maybe the default implementation, I have an idea. Maybe we provide a couple of 64-byte blocks per thread, and the idea is that you can have up to 2 things in flight at a time. But I haven't thought too hard about what the default should be, so that's just how that goes. Also, I've been thinking about a new name for libhal-exceptions. With this thing shrinking, I'm considering a new name. And I just want to go over a couple of names I think are bad. One is anything with near point in them, because near point is an idea that we have currently, or an idea I have currently. But if we find a better solution, which I think we might, then this will become historic, and then it'll just become like, an interesting name, but doesn't actually fit what the project is about. I considered looking at some of the things that I've made in terms of changes, like making this runtime single phase. But again, I want to support both 1 and 2 phase exceptions. Even if people decide never to use 2 phase anymore because I don't think it's useful. Maybe no one else finds it useful either. I still think that trying to give it this name is not a good idea. Especially if we ever find out that in some cases we actually need to use 2 phase, then that doesn't fit our name anymore. Any names pertaining to performance, like fast exceptions, are kind of cringe, because what happens if we're not actually the fastest anymore? Like, then what's our name mean? So, let's say OpenAI. Like, OpenAI is funny because they're not open. I mean, they made one OpenOS, but like nothing else about them is open. Their AI is very closed. So, I don't want names like that. And then finally, I don't put my own name in here, but basically I wanted to say like anything with my name in it as well. I'd rather it have a name that like fits a little better. And anything pertaining to memory size. So the idea of the names are like something close to libunwind, because that was actually one aspect of libhal-exceptions that's different from libunwind, which is that it's written in C++, and it was written in C++ built with the hopes of being as fast as absolutely possible. So I was thinking libunwind CPP, libcpp unwind, or libunwind++. If you're in the Discord, please tell me if you have any particular suggestion on these. I'm planning on actually archiving the current libhal-exceptions, creating a new repo fresh to bring over the libunwind CPP stuff, or libcpp unwind, or whichever one. Bring over the new exception stuff, so that any other libraries that are using libhal-exceptions can just continue using them as they were. But this new one will be focused and tailored just to being a good runtime. So yeah, that's pretty much that, I believe. Yes. Let's see what time we got. Cool. llvm-toolchain updates. I'm trying to get through this. I know I've already spent quite a bit of time. We now support ARM Cortex-M builds. Why have I done this? This is, actually, let me go back a little bit. We now support and enable semi-hosting by default on ARM Cortex-M builds. Why have I done this? This is to allow Conan test packages to link. One of the issues that I had with ARM GNU toolchain, as well as this one, was that anytime I tried to build a test package, it would go, oh, I can't find the write function, or I can't find the exit function, or I can't find the abort function, those type of things. So there are a bunch of C APIs that need to be around in order for things to work. The problem is, what if a test package uses printf or assert? With an operating system, you just link against the operating system's libc. With bare metal, linking failed due to missing low-level C APIs. For GCC, or the GNU toolchain, there's this specification called Gnosis, which provides empty or failing versions of the low-level C APIs, but just enough to link. And one thing I'm noticing is that whenever I've worked on this type of problem, there is no way with Conan's mechanisms to get around this. You need to have some way that the toolchain can default things to allow things to just link. And then provide escape routes for those people, for people who don't want that. But hopefully the main thing you give them is something that actually is workable without needing an escape route, because escape routes are kind of annoying to do. So in order to get this libc linking happening, I've enabled semi-hosting. Now, some cool benefits. Semi-hosting is kind of neat because it basically allows you to interact with your laptop, the device that you have connected, over a debugger. It is meant for debugging. It allows you to do print statements before you even have a UART developed for your chip. So you can print stuff using it. It will print out on the PyOCD side. Allows users to access files on the host. If you want to, you could literally look around and inspect things and suck up data and make files and that kind of thing. Yeah, it just makes things available on the host, on the device, as if it was another host. So some cons. Some small ROM loss to the semi-host initialization code. It's not that much, so I don't think it's that big a deal. It requires that the debugger be attached to the program as to prevent it from hard faulting. We have a workaround, but this was really annoying and kind of concerning when I was first dealing with this, because it would be really awful if you needed a debugger always attached for the code to work. And then finally, we have picolibc's implementation of semi-host can be very slow. I've seen fast implementations of semi-host that buffer data and all that, but it can take like 3 seconds to print out hello world, which is quite slow. Really only useful for like initial debugging until you get something better like a UART or a USB going. Along with that, there are some updates to ARM-mcu to support LLVM. This is all just to show you the work that I did in order to make it work. I had to update all of the linker scripts to no longer include picolibc, but to just set some flags and then set those flags for picolibc before putting it in. Basically, ARM decided to add a boot flash and boot flash size parameter or variable into their linker script, and they depend on it. So without that, things don't work properly. It'll link, but it'll sag fault immediately because the boot flash was set to 0 by default. So because there's a divergence between GCC and LLVM, we now need to have new linker scripts for these. And in order to accommodate the semi-host issue, basically anytime there is an API that tries to access the debugger from software from semi-host, we actually override the hard fault handler in order to detect these situations and then just simply return. If it's not that, then it loops forever. If you're concerned that like, well, what if I want to control my own hard fault handler? You can use the Cortex-M enable interrupt function and just replace it. So you can always replace that runtime, but the default built-in is going to do all of these instructions. I got these from Seger and then modified them to work for Cortex-M0 so that all these instructions would just simply work. And yeah, every time you set up or interact with the debugger using semi-host, it will cause a hard fault, and then this will escape the hard fault. This should only need to happen once at initialization before if you don't have the debugger connect up, and it'll never happen again until you actually have a hard fault. And then finally, this is actually supposed to be on the previous slide, just talking about getting support for LLVM. But anyway, decoupling libhal-exceptions. So rather than depend on libhal-exceptions for terminate override code, I've brought that code into libhal-arm-mcu directly. I've also am overriding the standard set terminate function. The reason why is that I want the users using our library to be able to use the typical C++ APIs for setting and getting the terminate handler. Getter works as is, don't have to change it, but the setter tries to pull in the default verbose exception handler, terminate handler. So I have to override that to get rid of that. And with that, that all just works. So before we had HAL set terminate and HAL set or get terminate. Now we just use standard. This makes things a lot easier we don't have to have more APIs. So yeah. And then finally, with LLVM, now when if you want to build the demos, you might have to do build missing at the moment, but you can just do HAL-mcu STM32F103 with LLVM as your toolchain, and it'll build. We're getting towards the end. We have libhal v5 updates. Basically, I've brought in strong pointer, async, and MP units. MP units got done today, or at least got it working. I need to make a PR and do some other things, but I'm happy that I at least have a working version that has a clean change. But for strong pointer, I'm just going to show you what it kind of looks like in implementation. I'm making a big change to how we do callbacks in v5. Same thing in async context and everywhere else. I'm getting rid of in-place function, and I am not going to use anything like std function or any of like function 2 or any other like function wrapper. I realized that std function will dynamically allocate, and it's doing that because it needs to know the lifetime of the object that it's the callable that it has. In place is great, but you're fixed in the amount of memory that you have. We are already using interfaces. We are already using strong pointer, and we want ownership of some sort for our callbacks. The other two either did it with heap or with std function, or contained it within itself, which meant it had more memory. All the things that we need are just single API VTable stuff. I need to actually add in the destructor here. But anyway, all callbacks in libhal are going to be replaced with interfaces. And they're probably just going to have a single API here. And I may even remove the tag here because that might no longer be necessary, since I should be able to disambiguate the schedule function based on it coming from the timed interrupt callback class. Anyway, the idea here is that in this example here, we import strong pointer, make it available so everyone else can use it. The timed interrupt for v5 will take a optional pointer to a timed interrupt callback. Whoever implements the timed interrupt callback will simply implement schedule. I do have an idea to make creating these implementations simple by even like passing in a lambda and having that automatically just kind of handle itself. I can add a mix in here that like allows it to immediately be cast and all that. There's fun ways to make this ergonomic. This is an optional pointer because I want the user to be able to pass in a null pointer, and that means that we're unscheduling, we're turning off the schedule. Just like how we had with optional in-place callback. I'm sorry, optional callback, which used in-place function. Next up, we have async context. Import async context. We can see here, this is the before. I'm sorry, I still have the import module stuff in here, but yeah. Before, the APIs didn't change. Now they return back async future of whatever value you have here, and they all take a first parameter of a context, which you don't need to set the name for if you're not actually using. Actually, in general, you don't need to set the name unless you're actually going to access it. I guess I want to repeat one thing that was asked or brought up before in a previous meeting. Does it seem like this is overkill in order to make the driver frequency and driver cycle, duty cycle for this PWM channel to be a feature? And I do expect that we will have implementations of PWM that talk over I2C, or talk over SPI, or talk over something that uses a DMA channel of some sort and has a time delay and has an interrupt that comes afterwards. If this implementation is synchronous and does not need to do anything, it is also, even better, a single doesn't need to call another coroutine underneath, then calling this function is as expensive as passing 2 pointers to it, and that's it. Yeah, so it ends up being as fast as doing a normal virtual call, because in C++, you don't know if something's actually a coroutine unless you know its implementation. So if it's implemented as a normal function, it'll operate like a normal function. You just call it, you get back a future that already has a value in it, and you're good to go. No coroutines necessary. Same thing with this function here. You get it back, and you realize it has nothing to continue. You're done. And then finally, I don't have anything special to show for MP units. I just got this done and figured out this morning. But basically, previously it didn't support freestanding targets along with modules. The long story, but basically you need to propagate some build variables down. I worked on a PR with a fix, but after that fix, we now can basically import MP units, and I can also see the symbols for MP units, so I can start bringing it into libhal. I gotta figure out how to actually build out the units that I want to. And that's pretty much it. I know that was a long one, but I'm actually just really excited. I'm going to go back to the beginning real quick and just say that like I spent a lot of time this last month, I think even 2 months, venturing into modules, improving CI, improving the code base, improving the build system support, trying to improve the exception stuff, all of that. Hopefully in such a way that not only does this help libhal, but also can help other projects that want to work with C++ and want a better way to go about doing things. Oh, and last thing I want to say is after realizing that this is the scheme that I want to use for libhal-exceptions or libcpp unwind, this is how I will write my paper for the committee. I'm going to provide a new user-defined allocator. The specification for compilers is that when a exception runtime needs to allocate for an exception, it'll call these APIs, and that gives the user control over this. One user on Reddit was asking about MSVC and how, actually, they weren't asking about that directly, but effectively, MSVC, I believe, uses the stack until it needs to move the object off the stack in order to keep its lifetime around. And this would still work for them because they would just call new at that later time. They could skip calling it completely beforehand. And yeah, that would pretty much be it. There'd be some sort of standard exception allocation tag. You'd implement this, and then you'd now have your own user-defined exception allocator. And I think that's the cool thing is that this is simple to implement. It's a library-only feature, actually. It'd be very simple to add in for LLVM and for GCC. Only issue with GCC is that it uses C bindings, but we can bind this. There's no issue there, so I'm not concerned about that. Yeah, overall, I think this would actually be like a slam dunk, easy thing because we can implement it rather quickly. It doesn't require a language change. Yeah, and that's pretty much it. That's it for this week, and hopefully I'll see you guys in 2026.